All right, so these carboxylic acids, Tina, what's the answer for C? Tina? Don't hear you, Tina. Colby, what's the answer for C?
For C, I had pentanoic acid.
Yep. So it has a carboxyl group. That tells you it's a carboxylic acid. It has 5 carbons, no branches, so pentanoic acid is correct. LJ, what's D?
2-methylbutanoic acid.
Yep. Again, you can see the carboxyl group. And 1, 2, 3, 4 carbons in the parent chain, so butanoic acid. Starting from the carboxyl group, the second carbon has the methyl branch. And F, Alex, what would you say there?
I said 2-methylpropanoic acid.
Not quite. Want to look one more time and fix your mistake?
Oh, 2-chloropropanoic acid.
Yes. Okay. How much of this stuff do you think you'll remember by July 10th? Okay, I'm going to email everybody a quiz mid-July, and we'll see how much you remember. Okay. Question number 11. Let's draw some of these real quick. 3-ethyl pentanoic acid. So here's what goes through my mind. Pentanoic acid, that's a carboxylic acid with a 5-carbon chain. So 1, 2, 3, 4, 5 carbons with a carboxyl group. You could put the carboxyl group at either end. 3-ethyl. So if I put the carboxyl group on the right, I have to start counting there. 1, 2, 3 ethyl with a 2-carbon branch. 2-bromopropanoic acid. Again, I see propanoic acid as a carboxylic acid with 3 carbons. This time I'll put the carboxyl group on the other side. And 2-bromo, so the second carbon has a bromine atom attached. 2,3,4-trimethylhexanoic acid. It's a carboxylic acid with 6 carbons. 1, 2, 3, 4, 5, 6. Carboxyl group. And then 2, 3, and 4 have methyl branches. 2, 3, and 4. Okay. Esters. Let's go down to number 18. Give the names of the acid and the alcohol, draw the ester, and then name it. Grace, what's the acid's name?
Butanoic acid.
Mm-hmm. And Vanessa, the alcohol?
Pentane 1-ol.
Yep. And again, just to remind you, when we are doing esterification reactions, we're only going to look at the primary alcohols reacting. It doesn't have to be, but that's what we're going to look at just because it makes the esters a little bit simpler to make. Do you remember what happens in the esterification reaction? In the acid, it's going to lose the OH, isn't it? And in the alcohol, it's going to lose the H. The H and the OH will get together and create water. So water is a product. And then where the acid lost the OH, it's going to use that carbon atom to bond to the oxygen in the alcohol, isn't it? So when I draw the ester personally, I find it easier to draw the acid part first. So 1, 2, 3, 4, and then I put the beginning of the carboxyl group. But then instead of a carboxyl group, it has an oxygen with the alcohol part attached, which had 5 carbons. So 1, 2, 3, 4, 5. 2, 3, 4, 5. I tend to have to double check just to make sure I put the right number of carbons there. Okay. And the name of this ester, Sarah, what would you call it?
Pentyl butanoate.
Yes. Do you find yourself naming it because I forced you to think of the names of the acid and the alcohol? Does that help to name the ester?
Yes.
Because on a test, I could just show you the ester, right? And just without anything else, what's the name of that ester? And then you have to look at it carefully and say, I know it's got the 2 pieces. This piece with the double bond, oh, that was the carboxylic acid. And the rest of that was the alcohol. Okay, so 1, 2, 3, 4, 5. The alcohol had 5 carbons, pentyl, and 4 butanoate. Right? So it's a little bit harder when you're just looking at the ester molecule. All right, let's leave the esters, go down to, well, how about that guy right there? Part E on the next page, question 21. This is what I was just talking about. It's a little bit harder to name the ester just on its own. Can you do that? Rachel, do you want to give this a try?
I have pentyl propanate.
Very close. Maybe you're just mispronouncing that a bit. Pentyl, because the alcohol part is this, isn't it?
Yeah.
And then you said propanate. maybe you're just mispronouncing it.
Yeah.
Propanoate. Right?
Yeah, that's what I meant.
Make sure there's an O there, right?
Okay. Yeah.
Okay. So good. So the alcohol there was pentane 1-ol, right? And the acid was propanoic acid. And then we left off with ethers. An ether is like an alkane, isn't it? But you broke the alkane into 2 pieces and you stuck in an oxygen atom to join them. That's basically what an ether is. There's an alkane with an oxygen somewhere in the middle of the chain. So we drew some of them. Where are they? Here they are. So question number 27. D. Madeline, what do you call that? Look at the last few examples to help.
Yeah. Maybe ethyl, 1, 2, 3, 4, 5. Ethyl, hexyl ether.
Isn't it 5 carbons? 1, 2,
Yeah, sorry,
3,
pentyl.
4, 5, right?
Yes,
Ethyl,
ethyl, pentyl, ether.
pentyl, ether. Yeah. Okay.
Mr. Patnode,
Yes.
would it have mattered if we said pentyl ethyl ether?
Well, in the real world, probably not. But according to strict UPAC rules, why is this one the right one?
Alphabetically correct.
It's alphabetical, right?
Oh, okay.
Sort of like branches, alphabetical.
Okay, thanks.
You're welcome. And Karen, what's E?
Dipropyl ether.
Yeah. And the last guy there, F. Emily, what's F? Emily.
Hexylmethyl ether.
That sounds right to me. Hexyl methyl ether, right? What are some of their formulas? Remember I said these are like alkanes with an oxygen stuck in the middle, right? So when you look at D, ethyl pentyl, isn't that 7 carbons total? 2 plus 5. So then the formula would just be C7H16. There's the alkane with an O. Dipropyl ether. How many carbons are in there? C what?
Six.
C6.
So how many hydrogens if we're thinking that it's just an alkane? C6,
14.
14, but then it's an
O.
ether. So there's an O in there as well, right? So it's just an alkane with an O stuck in there, right? Hexyl methyl, that's going to be 7. So C7H16O. And then you notice that that one and this guy are what? D and F.
Are they structural isomers?
They are. And in addition to the ethers, these 2 ethers, you could also make a whole bunch of alcohols, couldn't you, with C7H16O? Right? Alcohols are also structural isomers of ethers, because you could think of this as C7H15OH, couldn't you? It's the same formula, right? With an alcohol group instead. So ethers and alcohols are structural isomers, right? When they have the same formulas. Okay, flip down, let's do something new. This is there are a lot more functional groups. This is the last couple of our functional groups that we're going to look at. And then there's another class of molecules and we'll be done. So you've probably heard of these in your biology class, ketones and aldehydes. They're distinguished by having a C double bond O, which some people, I like to pronounce a carbonyl group. Other people will pronounce it as a carbonyl group. I usually say carbonyl. So a C double bond O is a carbonyl group. If that carbonyl group is at the end of a carbon chain, that's right, so it's at the end, then it's considered an aldehyde. The molecule is considered an aldehyde. So when it's on a terminal carbon atom, terminal just means at the end of the chain. If the carbonyl is not at the end of the chain, but it's somewhere inside the chain, so not on the first or last carbons, then the molecule is referred to as a ketone. Okay, so in the aldehyde, there's a carbonyl. There has to be a hydrogen because it's at the end of the molecule. And then there's an R group. That R group could be another hydrogen, in which case you'd have the simplest possible aldehyde, or it could be some kind of carbon chain. For ketones, the 2 R groups don't have to be the same. That's why they say R1 and R2. And they cannot be hydrogens, right? The 2 R groups here have to be carbon atoms so that the carbonyl is in the middle of a chain. Now, when you name them, the aldehyde's name, you have to really, really, really pronounce it, like overemphasize it. Otherwise, people will think you're talking about alcohols because it's like an alcohol, but instead of ending in all, it's going to end in al. So like if you have 2 carbons and it's an aldehyde, the name would be ethanal. 3 carbons and it's an aldehyde, propanal. So you really have to emphasize that. Otherwise, people will hear ethanol or propanol. So this molecule here, let's take a look at it. Do you recognize that that's an aldehyde? I see a carbonyl group, the C double bond O, and it's at the end of a chain. So that's an aldehyde. Well, then how many carbons are in the parent chain there? It's a little bit unclear. This thing at the end is a chlorine atom. You might want to fix that. So the parent chain here is what? Whoops, is 1, 2, 3, 4, 5, 6, 7 carbons, isn't it? So look at the name down below. Heptanal, okay, heptanal, Al. 2-methyl, because there's a methyl branch on the second carbon. So 2-methylheptanal. But there's that chlorine on the 7th carbon. So 7-chloro-2-methylheptanal, the full name. Why don't you need to put a number in the heptanal? Why don't you have to say heptan 1-al?
Because it's in the end.
Yeah, it has to be at the end, right? If it's an aldehyde. So you don't need to number that. But that carbon atom where the carbonyl group is, that will always be carbon 1, right? And just like you number from the end closest to the functional group. In aldehydes, the carbon with the carbonyl group, that's the carbon 1. Okay. Ketones, again, you see a carbonyl group. There's a carbonyl group, but it's not at the end of the chain. It's on the second carbon, isn't it, in the chain? The parent chain here would be 1, 2, 3, 4, 5, 6 carbons. There's a carbonyl on the second carbon, which makes it a ketone with 6 carbons in the parent chain. So look at the name, hexane 2-one. Why do I need to put the 2 there? Why do I need to say hexane 2-one?
Because it could be anywhere in the molecule.
Well, with hexane, where could it have been?
On the 3rd.
Yeah, the second or third, right? Everybody with that? If you count from the other side, second or third, second or third carbons, that's about it. So you have to tell me which one. So hexane 2-one. And then once you're counting that end, second carbon, you count from that same end and say there's a methyl branch on the 5th carbon. So 5-methylhexane 2-one. Logical? Any questions about that name? All right, well then, let's try a couple of simple examples. The prefix form, F-O-R-M, it's an old name. It used to mean 1 carbon. I don't know if you remember formic acid we talked about yesterday, the fire ants spraying it out of their butt. That was the same as methanoic acid, formic acid. Formaldehyde is an aldehyde, as the name suggests, with 1 carbon. That's what form means. So then what's its proper name if it has just 1 carbon?
Methanol.
Yeah, methanal. And then draw it. Well, you can't really draw this with a bond line formula. So just put a carbon, double bond O, and then you either just put 2 H's like that, or you could just even do that. It's such a small molecule. Okay, either one of those would be fine. Another old name, you'll see it in biology, is acetaldehyde. in the old naming system meant 2 carbons, like acetic acid has 2 carbons. Acetaldehyde is a 2-carbon aldehyde. So then what's its proper name?
ethanol,
Now,
Yeah, ethanal. Okay. And then its structural, it's right there, right? Give its proper name. Acetone, this one's a little bit weird because we just said acet means 2 carbons. But here, one is like the carbonyl group, somewhere in the middle of a chain. So acetone must be a ketone just from its name. And so if there has to be a carbonyl in the middle of the chain and it says acetone, then it's saying there's 2 carbons, again, acid, 2 carbons, attached to that carbonyl group, right? That's the logic. But it has to be in the middle of a chain. So then there has to be a methyl branch on each end of the carbonyl, doesn't there? So then what's its proper name? Was that a bit too confusing for you? So there's a carbonyl group, and then there's 2 carbons attached to this. So one of them here and one of them there. What's its proper name?
propanol,
Yeah, so careful. Did you say propanal? Remember,
Propanone.
this is a ketone now, not an aldehyde. So it'll be propanone. Do you have to say propane 2-one?
No,
Because that's the only
that's the only
place.
place to be.
Yeah. Is there a methanone? Can you have methanone?
No. Wouldn't that just be an aldehyde?
It would be an aldehyde, right? Not a ketone. Can you have ethanone?
No.
No.
Same logic, right? So propanone, that's the smallest ketone, right? Because you have to have a carbonyl in the middle of a chain. So there has to be at least 3 carbons. What's the first ketone that would require a number to say where the carbonyl is? So propanone, you don't have to say propane.
Butanol?
Think about that. Would butanone need a number?
Wouldn't it be pentone?
no,
So there's butanone. If I put the carbonyl there, and someone else puts it, somebody else puts it 1, 2, 3, 4 there. Are those different molecules, Dimitri?
That was Max, but no.
No, if you just turn it around, it's
Yeah,
the same.
Yeah, I thought that was Dimitri saying that earlier. Yeah, so butanone doesn't need a number either, right? So the first one that we would need it is pentanone, wouldn't it? Pentanone, the carbonyl could be on the 2nd carbon or the 3rd carbon. So pentanone, you would need to say pentane 2-one or pentane 3-one.
Mr. Patnode?
Yeah.
If like on a test we were to write the number when it like isn't necessary, would it like be marked wrong?
It would depend how early in the marking and how many drinks I've had already. Okay.
All right, thank you.
And how much chicken curry Hisham had brought for me. Okay.
Can I get marked first, please?
I didn't say which end would
Second.
be the good end there, Dimitri, right?
Yeah, but you'll get tired after all of us.
And have I mentioned, Dimitri, that I also like pierogies and halapshi?
Could you please send me your address?
So what else, Dimitri? Pierogi, halapshi, those are the only 2 Ukrainian things I know. What else is there?
Well,
There's also borscht.
Oh,
It's like a
borscht.
Ukrainian.
Okay, borscht, yeah. Like
yeah,
beef.
that's what I ate this today. Yeah.
Oh, I'm not a big fan of borscht there, okay?
Oh, I just didn't try real one.
Okay, fair enough. All right, let's move on. How about number 36? Let's just try a few of these. So when you look at these molecules, the first thing you should look for is the functional group, right? So when you look here, you see a carbonyl group. Then what do you say? is this an aldehyde or is this a ketone? What is this?
An
An
aldehyde.
aldehyde.
That's right. So now that I know it's an aldehyde, go ahead and name it. It's a little blurry, but those are all carbon atoms and methyl groups. Is that 2-methyl octanol?
Yeah.
What about the next one? Do you see a carbonyl group again? There's the carbonyl group. So is it an aldehyde or is it a ketone?
Ketone.
Ketone.
Okay, it's not at the end, so it's a ketone. We've seen this one before. This is the butanone, isn't it? In C, this is a chlorine atom at the end, so be careful there. Max, is that a ketone or is that an aldehyde?
Ketone?
I agree. And what's its name, Max?
Is it 1-chloro, 3, 3-one?
3
Or
O.
3 pentone? Pentanone?
Okay, that would be the American way to say it. 3-pentanone.
Or, sorry, 3-one.
Pen-
Pentan 3-one.
Pentane,
Yeah.
3-one. Okay, so make sure you're not just saying pent 3-one. It's pentane 3-one, right? The next one's a little hard to see, but this is the oxygen atom, and these are methyl groups. It's hard to find these older ways of drawing the molecules now that computers exist, but you'll still see these once in a while. So I stole this off the web, but it's not a very good quality image. Who haven't I bugged here? Jackie, what's the name of this thing? Well, first of all, aldehyde or ketone, Jackie?
It's an aldehyde.
Yep. And what's the name of it?
3,4-methyl.
Careful, 3,4 what?
Methyl? No, a dimethyl.
Dimethyl. Then what?
Hexa. Al.
Hexa-al.
Yeah.
Hexa-al.
Hexanoal.
Hexanal.
Oh.
Okay, so you just take hexane, you drop the E, and you add al, just like hexanol, right? Does that make sense, Jackie?
Yes.
Okay. Let's leave that for now. How about well, I should do one more. How about J? Looks a bit funky. So this is a H3C, CH3, H3C. I think the rest of that is visible. So what is that? Is that an ether? Or sorry, is that an aldehyde or is that a ketone?
Ketone.
That's a ketone, yeah. Now where's the parent chain? 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe? 9 carbons. And then I see 2 kinds of branches. I see 1 carbon branches and I see a 2 carbon branch. Put it together. Are you glad your parents didn't name you that? 4-ethyl 2,5-dimethyl nonane 3-one. Anybody disagree with that?
Mr. Patnode,
Yes, sir.
I have a question about E. I know we're not on E, but I have a question about it.
Okay.
So like when like naming it, since it has like a chlorine, and it has an ethyl branch,
Okay, so,
I think.
so this carbon is, this is the parent chain, right?
Yeah.
You could also have gone down. So we number from the left side, closer to the ketone, right, to the carbonyl. And then there'd be an ethyl and a chloro. So who gets named first?
That's what I was gonna ask. Is it still?
When there's different kinds of branches, how do you decide the order?
Is it still alphabetical?
Yep, yes it is. So this will be 1, 2, 3, 4, 5, 6, 7, 8. So this will be 8 chloro, right?
Mm-hmm.
3 ethyl.
Yeah.
Octan 1, 2, 3, 4 only.
Oh, okay, yeah, that makes sense. Thank you.
So you just name them alphabetically. Yeah.
Oh, okay.
And now I skipped F, but can someone guess what F is called?
Cyclopentane something.
You're almost there, Dimitri. Now you got to finish it. What?
Penthanone.
Good job. How many remembered cyclopentane? This morning, everybody forgot that. Cyclopentane. Well, why is it a ketone and not an aldehyde?
Because it's got no end.
It has no end, yeah. The carbonyl group has 2 other carbons attached, doesn't it? So it's got to be a ketone. So cyclopentanone. Why doesn't it need a number?
Because it's a cycle. It has no end.
Well, whichever carbon in the ring has that ketone, that's carbon 1, isn't it?
Yeah.
So if there was a branch over here, that would be 3-methyl, wouldn't it? 3-methyl cyclopentanone. Okay. All right. Aromatic compounds, our last category. This one's going to be confusing, okay? Confusing, not so hard to name, but hard to understand exactly what this is. So aromatic compounds, and I'm going to make a bit of an oversimplification. I'm going to say something that's not technically true, but for grade 11 chemistry, it's good enough. Aromatic compounds are molecules that have 1 or more benzene rings. This weird thing you're looking at is a benzene ring. It's benzene. That molecule is benzene. And as far as we're concerned, aromatic compounds are benzene derivatives. They have benzene in them. There are other aromatic compounds, but we're not going to consider them. So for us, these are molecules with benzene. Now, what makes this so hard to understand? It looks a bit weird. It's a 6-carbon ring. So it's always a 6-carbon ring. There's no 5 carbons, 6 carbon, 7 carbon. It's a 6-carbon ring. What's weird about it? Well, the way it's drawn, and in fact, the way it's labeled too, suggests that it has these alternating single and double bonds, right? Single, double, single, double, single, double. That's how it looks. And if I built the molecule with a model set, that's how I would build it. Single, double, single, double, single, double in a 6-carbon ring. But there's a problem with that. Make a note for yourself that a single bond is weaker and also longer than a double bond. Single bonds are weaker, double bonds are stronger. So because a double bond is stronger, it pulls the carbon atoms closer together. So a double bond is shorter than a single bond. It's not here, but a triple bond would be even shorter and stronger than a double bond. So why is this weird? Why is this so? Okay, let me just say, you will not understand what I'm about to say. Okay, you will not understand it. But let's try. When you actually measure the lengths of the bonds in benzene, you use a process called X-ray crystallography to measure the distance between two carbon atoms. You don't see long, short, long, short, long, short like this suggests. Instead, what you actually see is 6 equal bonds. So when you measure the lengths, the 6 bonds are identical. But they are shorter than single bonds, and they're longer than double bonds. In fact, they're kind of like the average of the single and double bond lengths. How can that be? What's going on? Well, what I'm going to say next is also not really true, but it is a way to sort of understand what might be happening, but just don't take this literally. You look at one of the double bonds. I've highlighted it here in blue. Think of that extra bond, the double bond. You remember every bond is a pair of electrons being shared, right? This double bond has 2 pairs of electrons being shared. Suppose one of those pairs of electrons is delocalized. Do you remember that phrase, delocalized? It means it can move around. It's not stuck in between those carbon atoms. So suppose this pair of electrons moves over there, forming a double bond over here. Well, what problem would that create? Anybody see it? What problem does that create? This carbon that I just put a star beside would now have 5 bonds, wouldn't it? Give me some feedback here with me.
Yes, do it.
If I moved that one pair of electrons from the double bond over here to make another double bond here, this would now become a single bond, right? Where the old double bond was. The carbon atom that I've starred now has 5 bonds, and it can't. It can only have 4 bonds. So then what has to happen? Well, then the pair of electrons that are in the next double bond also move and form a new double bond there. But that just moves the problem, doesn't it? Then this other electron's a pair of electrons in double bond also moves. And so what you'd end up getting is a new benzene ring with the double bonds like that, right? But that's still, it still suggests single, double, single, double, single, double. Well, imagine these electrons just keep moving around the ring, constantly moving around the ring. Well, then you could say on average, there's like an average of a hybrid of a single and a double bond. The problem with that picture is that if you imagine actually taking a picture of the molecule, even if the electrons are moving around the ring like I've kind of suggested, if you took a picture of it, wouldn't your picture have to show one of these 2 things, right? Your picture would show single, double, single, double. And if you measured the lengths, you'd find short, long, short, long. You don't get that. When you take a picture and measure the lengths, they're all average bond lengths and they're all the same. So that image I just created of delocalized electrons moving around the ring, it can't be literally true. What's actually happening here is a quantum thing. It's like you need some grade 12 chemistry, and even then you won't really understand it. So for now, let's just keep this in mind, that the electrons in the benzene ring and the double bonds are delocalized. And as a result, they move around the ring, so the double bonds and look like they're just moving to different places. You can draw down below the two versions of benzene with the double bonds moved around, right? So there's the two versions of benzene with a double bond, single bonds. You can also show it like this. You often also see benzene with a circle in the middle, and the circle in the middle is just meant to suggest the electrons are delocalized and moving around the ring, that every bond is the same, okay? So these are all ways of showing benzene. If you look back at the structural formula for benzene, every carbon has 4 bonds, 2 are a double bond and 1 is a single bond. So that means each carbon has only room for 1 hydrogen. So the formula is just C6H6. And with all those single double bonds, here's another interesting geometric fact. The molecule lays perfectly flat. So all 6 carbons and all 6 hydrogens, if you built this molecule and put it on your benchtop, it would lie flat. That nothing's coming up, nothing's going below. If you can look at my camera here for a sec, this is the cyclohexane. Cyclohexane looks like benzene, it has a hexagon. Can you see that? Has a hexagon, 6 carbons, but there's only single bonds. There's no double bonds in there. So every carbon has 2 hydrogens. And if you recall, there was an upside and a downside, then we had cis and trans, stuff like that. With benzene, that doesn't happen because there's only 1 bond for each carbon, and it's all flat. It's all, if you picked up a benzene molecule, like in the lab, a model of it, it would feel like one of those ninja stars, like in a Chinese movie. They throw the ninja star. That's what the benzene ring is like. Okay. All right. Take a look at question 1. So these are aromatic compounds. That's the categorization. They get that name because they generally smell. So chlorobenzene. So I see benzene and go, okay, it's got a benzene ring. This is an aromatic compound. I'll draw benzene in several different ways. There's one way. Chlorobenzene, there's a chlorine atom attached. Done. Why don't I need a number? Because whichever carbon the chlorine's attached to would be carbon number 1, so you don't need a number for that. What about B? 1,2-dibromobenzene. Benzene. It's an aromatic compound, so it has the benzene ring. This time I'll draw it like that. What does 1,2 mean here for dibromo? Somebody?
That they're next to each other.
That's right. So put the first one wherever you like. There's a bromine. And if it's 1,2, they just have to be on neighboring carbons. Okay, so if you draw a benzene ring and show 2 bromines attached on side-by-side carbons, that's correct. About ethylbenzene. Okay, a benzene ring, aromatic compound. Ethyl. Done. Two ethyl 1,3-dimethylbenzene. 1,3-dimethylbenzene rather. Okay, benzene ring. I think this name might be wrong. But anyways, 2-ethyl and 1,3-dimethyl. So 1 and 3-dimethyl, 2-ethyl. I can draw it. I think you're supposed to call the ethyl carbon 1, because that comes first in the name. If that's right, if you should have called ethyl carbon number 1, then what would the other ones become? 1 ethyl and then what? Somebody?
2, 5.
2, 5, right? Dimethyl. I'll double check that. Okay, and 1, 2, 5, the problem with that is those are bigger numbers, isn't it? Than 2, 1, 3. But I think you're supposed to name the carbon with ethyl on it first, because ethyl was going to be named first. We saw that earlier. So this one I'm a little bit ambiguous about.
Wouldn't it be 6 instead of 5 though?
1, 2, 3, you're right. 2, 6. Yeah. Give the names for these molecules, number 2. Try A. Who gets the 1 here?
The bromine?
Because alphabetically it goes first, right?
Yeah.
Then where's the chlorine?
3.
Very good. Go around that way to keep the numbers small, right? So the name would be 1 bromo, 3
chlorobenzene.
Benzene. Okay. If we name part B, like I said earlier, we have a methyl branches, and then what's the other branch? What is that?
Butyl.
Careful.
Oh, sorry, it's propane.
Propyl, right? And we're going to have 3 carbons, that's propyl. So we're going to name methyls first, right? So then the top methyl or the bottom methyl, which one's going to be number 1? Try to keep your numbers small. So the top one will be 1, and then the propyl will be
Second.
2, yeah, and the other methyl will be 4, right? So then the name is 1, 4 dimethyl 2-propyl benzene. Okay, so aromatic compounds always have a benzene ring in them. They can have more than 1 benzene ring, but we're not going to look at that. Number 3, and we'll finish with this in terms of new material. There's an old way of naming aromatic compounds when they had 2 branches, only when they have 2 branches. It used prefixes instead of numbering. The prefixes, as you see there, were ortho, meta, and para. And then you could even abbreviate those prefixes with just the letters O, M, and P. So OMP. Ortho is when the 2 branches are side by side. So it would be the 1, 2 numbering. Meta is when there's a carbon in the middle of the 2 branches. So 1, 3. And para, they're on opposite sides of the ring. So there's 2 carbons in between them, 1, 4. So if you heard of this molecule, we may have used that back in grade 9, I forget, or we talked about it before, para-dichlorobenzene. Well, that's benzene with 2 chlorines, dichloro. And what does para mean? It means they're on opposite sides of the ring, or there's 2 carbons in between. Right? So there's the molecule. The numbering name for that would be 1,4-dichlorobenzene. If I showed you that molecule and said, what's its name? You could use either system, the para or the 1,4. Try drawing A, orthodimethylbenzene. Benzene, dimethyl, 2 carbons, and then Ortho means, I just remember omp. Ortho, side by side. Meta, one apart. Para, two apart. So this is going to be something like that, right? And one last one here, meta ethyl methyl benzene. Notice the alphabetical order there, ethyl before methyl. And what does meta mean? What does meta mean, folks?
One
between the
carbon in
two.
between.
Yeah, there's going to be an empty carbon atom in between them, right? So put a ethyl there maybe, and put the methyl 2 carbons away. It doesn't matter which way you go. I'll put it, blah, stupid pen. I'll put it the other way around, like that. Okay. All right. Questions, folks, about aromatics?
Yes, and how big branches can we attach to benzene?
Things get a bit tricky there, Dimitri, because if I don't know specifically what the rule is, but if there is a really long chain and a benzene is attached, then the benzene at that point is named as a branch. And then its name changes from benzene to phenyl, PHENYL. So for example, if you imagine a 10 carbon chain and there's a benzene ring attached on the second carbon of the 10 carbon chain, you would call that 2-phenyl decane. But I'm not exactly sure how long the chain has to be before the benzene is looked at as a branch, or where the chain is thought of as the branch on benzene. I don't know exactly what the cutoff is there. Okay, so I'm not going to show you anything like that. All right, so folks, you don't have this. What we're going to do is just pick a few molecules here in our last 3 minutes. Look at the molecule. What type of molecule is this? And then what's its name? Don't bother drawing anything or writing anything, just look at it. What type of molecule is that?
Alkyne.
Triple bond, yes, that's an alkyne. Now that I know it's an alkyne, Hisham, what's its name? Hisham?
Yeah, would it be 3-iodo-propan 1-ine?
So not propane 1-ine, it's just prop 1-ine. Okay. So propane, propene, propine. So that you don't say propanine and propanine. Does that make sense?
Yeah.
Okay. What about that? Somebody other than Hisham. What type of molecule is that?
That's ester.
That's an ester, yes. All right, Dimitri, then what's its name?
It's ethyl butanoate.
Very good. That's one of the harder ones for people to name. So good job. What's that? Somebody other than Dimitri or Hisham.
Isn't that an aldehyde?
It is. So Madeline, what's its name?
2-chloropropanal.
Very good. 2-chloropropanal. Somebody new. What's that?
Is that a ketone?
Yes, it is. And what's its name?
Propanone.
Yep. What's its old name? That's still very common. That's acetone. It's found in some old nail polish removers have that in it. What's that? Somebody new. Nobody?
An alcohol?
Thank you. That's an alcohol, yes. Oh, I don't know who said that. Who was it?
Camille?
Sorry, Camille?
Yeah.
Camille, what's the name of this?
4,4-methyl or dimethyl. Wait, 1, 2, 3, 6 hexane. Wait, 1, 2, 3 hexane 3-ol.
Very good. Good job. And our last one for the day. I would not give this to you on a test. So can someone figure out what that's called? Be brave, be logical.
Cyclo 1,2-dimethyl cyclopentane.
Oh, you're close. You're very close.
Or the whatever the thing with the double bond. I don't remember what it's called.
Someone help him. It's
Dichlorocyclopentene.
1,2-dimethyl. Cyclo what?
Pentene.
Pentene. Yeah. With a double bond, it's an alkene, isn't it? So
Yeah.
1,2-dimethyl cyclopentene is what it would be called.
Can we call it ortho-dimethyl?
No. Ortho, meta, and para are only used on benzene. So make sure you've got that down somewhere. Those three prefixes, ortho, meta, and para, are only used for aromatic compounds with benzene rings when the benzene has two branches. This is not a benzene ring, so you're not allowed to use that. Okay? All right, folks, we're going to practice tomorrow organic nomenclature, sort of like we're doing here. I posted a 4-page document on Classroom with a whole bunch of molecules of different types. You don't have to do it all. Do what you want with that. I will post the answer key to it as well, and you can check your answers. What I would suggest is that you try to do exactly what we're doing here, classify the molecule, and then try to figure out its name. Okay, so there's a 4-page document on Google Classroom. Do with it what you want. Tomorrow we'll practice, and then on Thursday, probably in class, that'll be the organic chemistry test. Okay, it'll be a Google form test again. And then the final assessment will be due the following Tuesday. Okay.
Mr. Patnode?
Yeah.
For Monday and Tuesday of next week, do we have to be on Zoom with you, or is it just like a check-in?
What I think I'm going to do is, I'm not going to probably do attendance. What I'll probably do is I'll start a Zoom meeting, and I'll probably do this starting on Friday this week. I'll start a Zoom meeting if people show up for the first 5 minutes or so to ask questions about the final assessment or something. Then I will stick around and answer questions. If there's nobody here for the first 5 or 10 minutes, I don't see anybody, then I'm not going to hang around for the whole hour. Does that make sense?
All right, that sounds good.
So starting on Friday this week, you can show up if you have questions. If you don't have questions, you don't have to show up. Okay?
Okay.
All right, folks, have a good evening. We'll see you guys tomorrow.
Mr.
Have a good night.
You have a good night.
Take care.
Very good one.
Thank you.
Mr. Patnode,
Yes.
I had a question.
Alex, what's up?
This is more individual, so yeah.
Thank
I
you,
was
Mr.
wondering-
Before, like Alex asked his question, Nati asked a question in the chat, and I was wondering the same thing.
What was the question?
how long would the test be open for if we did it during Thursday?
It'll be done in class.
Okay, so we'd only have the hour to do it?
Yeah, it won't take an hour, but it'll be done during class time on Thursday.
Okay, thank you. Bye.
You're welcome. Take care.
Thanks. Have a good day.
Take care.
So
Yes,
I was
Alex.
gonna ask about the gases test and those two websites.
Remind me, did you
Because
miss?
because I was out for the concussion and then
Oh, that's right. So you had the concussion and I'm the one that forgot it. So we can do one of two things at this point, Alex. Okay, so I can excuse you from them. Okay. So, but that would be only based on, do you know how to make chicken curry?
no, but
Okay, so-
I could try and learn.
No,
I
I
guess.
don't want like some trial, okay? And I don't think pierogies or halapshi either, right? Like I'm trying to tiagli. What's the ethnicity there?
Ukrainian.
Oh, Ukrainian. What the hell?
Yeah, do you not remember when Dimitri just came, you put him in the group with me and Nathan so
No,
that
I
I could
don't remember
translate
that. I
so that I could
forgot.
translate to Ukrainian
I
when we were
forgot
doing
that.
the
And now that
yeah.
you mention it, I remember that. Okay,
Yeah.
I'm only joking, of course. So we can either excuse you from that. I don't mind doing that. If you'd like to actually, maybe once you've done the exam review, the final assessment, if you feel like you want to give it a try, you can do that as well. I'm guessing I know what you'd prefer to do.
I think you're guessing correctly. Yeah.
All right. So which day would you like to do the test on? Oh, sorry. I thought because you were such an exemplary student, I thought you were going to want to try to do the test. I guess I must have misread you. Sorry. I'm kidding. All right. So I'll excuse you from the test and from those two assignments. Okay.
Okay. Thank you.
All right. Have a good evening.
You too. Bye.